In this video, we're going to look at special angle triangles and how we can use those to solve various trig ratios in radians. Let's recall we have special triangles that involve degrees of 30, 45 degrees, and 60 degrees. In terms of radians, 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. There are two special triangles. There's our 30, 60, 90 triangle, and there's our 45, 45, and 90 triangle. For our 30, 60, 90 triangle, we have sides of 1, root 3, and a hypotenuse of 2. So if we take this angle here as our 30 degrees, or our pi over 6, this angle is our 60 degrees, or pi over 3, then we would have 1, root 3, and 2. An easy way to remember this is the pi over 3 angle is opposite our root 3 length of side. For the other triangle, 1, 1, and root 2, both of these angles are pi over 4, or 45 degrees. Now get used to thinking in radians. It's going to be very time consuming if you're constantly converting between degrees and radians. I know radians are weird, but the more you see them, the more you get used to them. There are some other key radian measures to remember, so let's put them in our circle here. We have 0 or 1 complete revolution is 2 pi, so halfway around is going to be pi. Halfway between those 2 points is going to be pi over 2. And the bottom one here is going to be 3 pi over 2. We have our angles of pi over 6, this one's pi over 4, and this one is pi over 3. Really, those ones are the only ones you need to memorize, and then just be able to understand how to get all of the other angles. So our next one here is our 90 degrees, or pi over 2, plus a 30 degrees, which is pi over 6. Pi over 2 plus pi over 6 is going to equal to 2 pi over 3. The next one is going to be our 90 plus our 45, which will give us 3 pi over 4. And let's just fill in the rest here, 5 pi over 6. For the ones down in this quadrant here, you could take, like for the first one would be pi over 6 plus pi, and that is going to give you 7 pi over 6. Next one is going to be pi plus pi over 4, which gives you 5 pi over 4. And the last one, 4 pi over 3. And finally, the last 3 angles are 5 pi over 3, 7 pi over 4, and 11 pi over 6. Now, instead of solving for trig expressions and equations in degrees, we can solve for them using radians. In general, to find trig ratios for angles greater than 90 degrees, or pi over 2, you need to find the related acute angles. And the acute angle is going to be the angle formed by the terminal arm of the angle in standard position and the x-axis. You can also use your cast rule to determine the sign of the trig functions. Now remember, our cast rule, C-A-S-T, tells us which quadrant each of the trig functions is positive in. Cos is positive down in that quadrant. They are all positive in quadrant 1. Sine is positive in this one, and tan is positive in this one. Our first example then asks us to find the exact value of sine of 4 pi over 3 and cos of 4 pi over 3. We first need to locate our 4 pi over 3, and that is going to be this angle down here. So we are looking for our terminal arm and the angle it makes between the terminal arm and the x-axis. Let's just pull our triangle out here. Now that angle is going to be pi over 3, so that means this is root 3, this is 1, and this is 2. To find the sine then of 4 pi over 3, remember our SOHCAHTOA. So sine is opposite over hypotenuse. It's going to be root 3 over 2. Because we are in the quadrant where only tan is positive, this is going to have a negative value. Cos of 4 pi over 3 is going to be adjacent over hypotenuse, so 1 over 2. Again, it's in the quadrant where only tan is positive, so this is going to have a negative sign. Example 2 says if -2, -3 lies on the terminal arm of an angle theta in standard position, determine the exact values of sine, cos, and tan of theta. Let's draw a quick sketch of what's going on here. So at -2, -3, the point's going to be down here. This will then be our terminal arm. So we're looking for the angle theta, so we're going to be looking at this acute angle here to get each of those three trig ratios. Our distance here is -2 and -3. So we need to figure out what the hypotenuse is in order to finish solving for this problem. So we're going to use Pythagorean theorem, and -2 squared plus -3 squared is going to be 4 plus 9, which is going to give us the root of 13. Okay, so now that we've got all three sides of our triangle, we can solve for each of our trig expressions. Sine, remember, is opposite over hypotenuse, so that's going to be -3 over root 13. Cos is adjacent, so -2 over root 13. And tan is opposite over adjacent, so that's going to be 3 over 2. This is positive because we are in the quadrant where tan is positive. To calculate the related acute angle in radians to 2 decimal places of the above, what we could do is take any one of our three trig expressions here and solve for the angle. So sine theta is -3 over root 13. That means that theta is equal to sine inverse of 3 over root 13. Now, you need to put your calculator into rad mode here, because if you leave it in degree mode, you are going to get the answer for theta in degrees, and we want it in radians. So take a look at your calculator. There should be a way to put it in radian mode. If you do that and plug that in, you should get 0.98 rad. If you don't get this answer, make sure you message me to ask me how to set your calculator in rad mode. Last thing that I just want to quickly review is that when working with trig ratios, when the terminal arm is on the axis, so either the x or y axis, it's a lot more helpful to use the unit circle to solve for one of these ratios. Recall the unit circle is a circle centered at the origin with a radius of 1. So if we draw on a radius here, our radius is equal to 1. If we wanted to find the point on that circle that it lies at, we could say it's a point x and y. If we've got our triangle here, we've got distance of x and distance of y. So looking at that theta, let's first look at sine theta. If we were to find sine theta, that is our opposite over our hypotenuse, which is 1, which is just going to be equal to y. Similarly, if we look at cos theta, that is x over 1, or just equal to x. So what this means, and it's a really nice relationship, is that any point on this unit circle can also be written as cos theta and sine theta. And that's because x is equal to cos theta and y is equal to sine theta. So this comes in useful when we have degrees of, say for example, 90 degrees, and you wanted to solve for either cos or sine theta. Then at 90 degrees, or pi over 2, your point would end up here on the y-axis at 0 and 1 on the unit circle. So a cos of 90 degrees, or pi over 2, is going to equal just our x term, which is 0. And sine of 90 degrees, or sine of pi over 2, is going to equal our y value, or 1. So each of these then becomes a nice easy way to figure out what the values of cos and sine are on the axes. For example then, find the exact value of sine of pi over 2. Sine of pi over 2 would be this angle here. This is going to happen at 0 and 1. And sine is the y value, so sine of pi over 2 is just equal to 1.